So we're going to finish up Newton's method here. We're going to look at one more example, and then we're going to look at some situations where Newton's method might fail. So the first example we have here, we're looking for the zeros of, and so this is going to be my, of course, f of x is our x plus cosine of x. And for Newton's method, we're also going to need f prime here at some point, so I'm going to go ahead and write that down. So that's going to be our 1 minus sine of x. Now remember, this is where in my graphing calculator, I'm going to store y1 as f and y2 as f prime. All right, now what we kind of notice here is we're not given an initial starting point. So from our graphing calculator, we're going to have to determine a good starting point. Also, this says approximate the zero, so I haven't yet determined if there's 1, 0, 2, 0. So all that's going to require that we're going to take a look at this on our graphing calculator. So in our y equals, let's go ahead and enter our x plus cosine of x. And first, let's just go maybe just a zoom number 6, zoom standard. And as we look at our graph, again, the visual on my graphing calculator, the graph display may look slightly different than yours, but I think we can all kind of take a look and say it looks like maybe that 0, that x-intercept, is near -1. So that certainly seems like a good initial choice. Now, the formula then for Newton's method is that previous guess minus f of that previous guess divided by f prime of that previous guess. So this is what we're going to have when we sub in for Newton's method, but we want to use our calculator efficiently. Let's go back to the y equals, and we're going to store 1 minus sine x into our y2. Now we're going to second quit to go back to the main screen. We're going to enter -1 first and hit enter, and then we call up that answer. So second and the little negative, and then we're going to do minus, and then the vars, the variables menu, arrow to the right to y variables, and yours has more options, but this has what I need, 1 on function, and then 1 on y1. It recognizes function notation, so left parenthesis, and then second answer, so that little negative sign, close parenthesis above the 9 there, divided by, and now for f prime, it's the vars menu, arrow to the right to y vars, 1 on function, and 2 for y2, because that's where f prime is stored. Again, the parenthesis, which is above the 8, second answer, and then close parenthesis and hit enter. So we have -0.75036 and so on. All right, so that's our x sub 2. I'm not going to write out the work here. Let's just call up second, enter, and do this again for x sub 3. So -7.391128909. I don't yet have two guesses. If I subtract these two, they don't differ by less than 1,000th. So we continue. And one more, second enter. And now I have -0.739. And then, 0.85 and so on. So these last two guesses, if we form their difference, they definitely differ by less than 1,000th. And so this is going to tell us then that our value here for our 0 is approximately -0.739. Okay, so that is how a typical Newton's method problem would work here. All right, so let's see if I can never get rid of this graphing calculator very easily. There we go. Okay, so let's continue and let's think about where Newton's method might fail us. So Newton's method fails in some other situations here, and that's what we're going to look at in the last part of this video. You could just be closing in on a 0 that's not the one you're interested in. You could come to an x sub I, one of your values in your sequence of those guesses, that's undefined because you get a 0 in the denominator. Now, if you have that happen and you think about what's happening there, this would mean that you would have an f prime of some sort of x sub I, one of these guesses, that was equal to 0. So if you think about what that means graphically, if I was trying to find some sort of, 0 or something, whatever the case is, maybe I'm trying to close in on this 0, and at some point I get to an x sub I here, where when we take it up to the function, the f prime is equal to 0. So it kind of makes sense, oh yeah, if the slope of the tangent line here is equal to 0, obviously that kind of terminates our pattern, because we're supposed to be taking that until the point that we get to an x-intercept of that tangent line. So, that could happen. Both 1 and 2, the first 2 bullets there, could possibly be remedied by looking at maybe a different initial guess. But this is kind of another issue, this third bullet. So a lot of times, not a lot of times, sometimes, maybe the 0 that we're trying to find, like in this case, it looks like there's a 0 at the origin. Sometimes if, let's say I start, and in this one, the first x in my sequence is denoted x sub 0. So I take that to the function, there's the point, I draw the tangent line, and I take that tangent line down to its x-intercept. Then if I take, that's my next guess. Then I take that to the function, and then I draw in that tangent line and take that tangent line to its x-intercept. That's my next guess. And you should feel how if you take this value to the function, draw its tangent line, take that tangent line down to its x-intercept, we are moving further and further away from that 0 that we're interested in. So that can happen too. All right, so what we're going to do on this one here is we are going to just take a look. We're going to do our Newton's method here. And so we start off and we have our f of x is equal to our x cubed minus the 3x squared plus 3x. And now we want to also, of course, find our f prime, and that's equal to our 3x squared minus 6x. All right, so on this one, I am told to let x sub 1 equal 1. And so if we do that, then our x sub 2, of course, is always the previous guess, minus, and then f of that previous guess. So f of 1, and then divided by our f prime, so f prime of that previous guess, so f prime of 1. All right, so in this case, I think honestly we can probably just do this particular one maybe just in our head and kind of just look at this computation isn't too bad, and we're only going to kind of take this iteration once. Because notice what happens. We get 1 minus f of 1 is going to be 1 in this case, and our f prime of 1, which I made a mistake on as I look back up, this should have been plus 3. Oops, sorry. And now when I sub that in, I end up with f prime of 1 equaling 0. Okay, so this is going to be a situation, obviously division by 0 does not exist. So this is going to be a situation when, our Newton's method fails. So Newton's method fails on that one. All right, let's take a look at one more example. I'll just kind of make this one brief here. Again, we've done so many of these by hand. I don't really want to spend a ton of time going through all these here. So here's our y, so x to the 1/5. And then if we were going to find our y prime, we would have our 1/5 x to the negative 4/5. And so if we were to start at our x sub 1 is equal to 1/10, our x sub 2, again, would be your 1/10 minus your f of that 1/10, and then divided by your f prime of 1/10. So this one, I took the liberty of kind of just plugging into my calculator earlier. So let's just kind of look at these values. We've done so many of these. Hopefully you're on to the idea of it. So I'm going to then just say, okay, so now suppose we continued. And if we were to do this, I want you to kind of be looking at the sequence of x sub I. So hopefully you got the idea down of how to do these in your calculator. And so here's the first 6 values that you would get. And so what you should notice is that these values are getting further and further apart. And they're also bouncing back and forth between positives and negatives, moving further and further apart. It's not like they're going positive to negative and closing in on 0. They're not. So you go from negative 4/10 to 1.6 to negative 6 to 25 to negative 102. So this is one of those situations, now we can see it numerically, when we might just say the sequence of x sub i's is not converging. And so this is another example where Newton's method fails. All right, so that's our last examples then in this section. And actually the last examples in this chapter, I do believe. So we've wrapped up section 3.5 here today.